Today we're going to discuss more on two-dimensional motion, but rather than discussing the linear motion that we went over it last time in the video, we're going to discuss circular motion. So still moving in two dimensions, but we're going in a circular path. Now, much like when we first discussed all kinematics and how we describe motion, we looked at what was called uniform motion, which was an object going in a constant speed in a straight line or with a constant velocity, same direction, same speed. We have a similar concept in circular motion that we call uniform circular motion. And, if you can make that analogy, it's similar in that it's a constant speed, but instead of a straight line, we're going in a circular path. Right, so for uniform circular motion, if we were to draw a motion diagram, it would look something like this, where we have a bunch of evenly spaced dots around that circle, and if we were to connect them with arrows representing the velocities, all of them would be the same length because it's moving at a constant speed. Right, now one thing that we have to be careful with here is remember position, velocity, and acceleration are vectors. They have magnitude and direction. So just because an object is moving at a constant speed does not mean it has a constant velocity. And this is one of those cases where our velocity is changing, right? The direction that that object's moving is different as it goes around that circle. That is a change in velocity. So just looking, in this visual representation and doing what we did before, we can sort of calculate, or think about what the acceleration of these of that object is as it goes in a circle. And basically, we could take two sequential velocity vectors, say this one and this one, and do the vector addition using those arrows. If you remember, so this would be v, we'll call it v2, and this would be v1, right? Because they go in that way. And the acceleration would essentially be that delta v over delta t, or that arrow would be v2 minus v1, how that velocity changed between those two instances in time, over some delta t. Time's going to be a scalar in this, so all the directions are going to come from the vector addition of those. So if we take v2, if we wanted to write this out, it would be some arrow that looks like, let me see how close I can draw this, something that looks like that. That's my v2. And then I want to add to it negative v1. So negative v1 is the same as this arrow, just in the opposite direction. So if I were to go tip to tail and draw that downwards, that would be my v1. And I'm trying to get as close as I can with the velocity. So if I want to take my delta v, which is going to be the vector that's in the same direction as my acceleration vector, it's just going to be this vector, v2 plus v1, and we know from that vector addition, I just go from where I started to where I end. That's my delta v, or my acceleration vector, right? And if I were to draw that over here, what I see is that vector points towards the center of the circle. And it turns out if you do these for any sequential set of vectors, v1 and v2, v3, v4, as we go around the circle, it's always going to be the same thing if we're in uniform circular motion. If that speed isn't changing, and the only part of velocity that's changing is the direction, as I go in a circle, my acceleration vector is going to be pointed at the center of the circle as I go around. Right, so this is much more neatly drawn than I could freehand. But that's what we get. All the acceleration vectors, when you're moving in a circle at a constant speed, point towards the center of the circle. And it turns out if you're going in a circle, even if your speed's changing, there's always going to be a component pointed towards the center of that circle, or the center of the turn. And the way we can, sort of think about this is it's often convenient to split up your acceleration into components like we would, but rather than, say, having a typical, let's call it X and Y direction, we can we can choose any coordinate system we want. But we want them to be at a 90-degree angle. And if they are, then we can do our components like we did in the previous lecture. But if we align one of those directions, call it a parallel, along the same direction that the velocity is in, and then that acceleration vector, the total acceleration vector, would have two components. If we defined our coordinate system to be in the parallel direction, so one of our directions is in the same direction as the velocity, one of our components is perpendicular to the velocity, that's our right angle. That's a coordinate system we can use. If we split this acceleration vector into components, one parallel to the velocity and one perpendicular, we can sort of see that what it means is those two components each change a different part of the velocity. The parallel piece is going to be changing the magnitude of that velocity vector. If there's any component of acceleration in the same direction as the velocity, that velocity vector is going to get larger or smaller if it's parallel. The perpendicular component describes the change in direction of that velocity vector. So in this case, this velocity vector is going to start turning to its left or up in the page because of that perpendicular component. It's often really nice conceptually to think about these ways, because the acceleration and the velocity in that relationship this way, because it sort of conceptualizes what part's changing in the thing, and it highlights, I think, the fact that just because the speed, the magnitude of that velocity is constant, does not mean there's no acceleration. We can change direction. That's a change in the velocity vector that we have to consider. So how is this going to affect how we describe motion? All right. So if we just take, a standard coordinate system where we have some y direction and some x direction, and we consider an object that's sort of going around in a circle, something like that. Oops, scroll down there. What does this look like? Right? Well, this object, let's say it's here, it's going to keep going around in the circle in that direction. Well, I know its position, is described by that vector r. I can split that into components x and y. And using what we did in the previous video, we would then consider breaking our kinematic equations for constant acceleration into components and solving them that way. But we run into a problem. What is the acceleration for this object going in a circle? Well, it has an acceleration vector pointed towards the center of the circle, as we just discussed, right? So it's that way. And then when the object's over here, that acceleration vector is now pointed down again, still towards the center of the circle there. When it's over here, it's got an acceleration vector pointed towards the center of the circle. But the point is, the direction of that acceleration vector is constantly changing as this object goes in a circle. And if you remember, what we derived, our kinematic equations, those are the kinematic equations for constant acceleration. So we can't use them in this XY coordinate system to describe this motion. We're sunk. We have to develop other tools or things to sort of describe this motion. And what we're going to use is sort of like a new coordinate system. Rather than describing this linear description of motion, we're going to use what's called an angular description of motion, because this object's going around a circle, and essentially, if I just keep track of how far that angle has gone, we're good. So the way we're going to define this is we're going to consider this path, this coordinate system, typically our x and y coordinate system. And if I'm moving along some arc length like this, where I'm here, I can define an angular position that's essentially theta. So theta is my angular position, and it's essentially the distance in some measurement of an angle along that circle. So if it's gone some distance s, call it that arc length there, and this is r, the radius of the circle I'm traveling on, this angular position theta can be written in the units of radians. That is just going to be the ratio of that arc length to the radius r. And that's the angle in terms of radians. But we can describe, because, we can sort of set up a description of motion in terms of this angular position, and then we can also just build on that, just like we did with regular position, and define an angular velocity. And we'll call that omega, another Greek letter. And just like we did with our linear velocity, it's going to be described as a change in the angular position with respect to a change in time. And if we wanted to go even further, we could go to the third level, and angular acceleration. Again, angular being the key word here, and we would use alpha and define that as the change in the angular velocity over the change in time. But you can hopefully sort of see that we're just going to do the same sort of thing we did with our linear positions and our linear velocities and our linear accelerations, but we're going to use these angular terms. And in that way, because this is all going to be following along that same circle, and this, the direction is, it essentially reduces this circular motion problem into, kind of an effectively one-dimensional problem where all we're concerned about is the direction in that angular direction. All of the steps we did deriving our kinematic equations for constant acceleration, we're going to mirror that and follow that here, right? We're going to look at this average angular velocity, which is the change in angular position over the change in time. We're going to take the limit as delta t goes to 0, and this is going to show that the angular velocity, instantaneous angular velocity, is the derivative of the angular position with respect to time. Likewise, that average angular acceleration is going to become the derivative of the angular velocity with respect to time. On a angular position versus time plot, right? The angular velocity is going to be the slope of that, because that's what the derivative is. Likewise, if we have an angular velocity versus time plot, the change in angular position is going to be the area under the curve, because we can just, from the fundamental theorem of calculus, take this, let's go back here, show that the change in angular position is the integral of that angular velocity with respect to time between those two times. And likewise with angular velocity. So we end up with, where I'm not going to go through all those derivations right now, they're in the book and they exactly mirror what we did for the linear velocity stuff. We end up with the analogous kinematic equations for angular position and angular description of motion, where we have the final angular position is equal to the initial angular position plus the initial angular velocity times delta t plus 1/2 the angular acceleration times delta t squared. We have the final angular velocity is equal to the initial angular velocity plus the angular acceleration times delta t. And that third one, the final angular velocity squared, is equal to the initial angular velocity squared plus 2, the angular acceleration times the change in angular position. Oftentimes you'll see this first one here just rewritten in terms of the angular displacement, which essentially you just bring this initial angular position to the other side, and that equation becomes the change in angular position is equal to the initial angular velocity times delta t plus 1/2 alpha delta t squared. But the point is, we have the three kinematic equations for constant acceleration. Now we have the angular versions of those where they're the exact same. You just have to put angular in front of all those descriptions and acknowledge these aren't this isn't going to be in meters. It's going to be in degrees, or more appropriately, radians. The angular velocity isn't going to be in meters per second. It's going to be in radians per second, or revolutions per minute, or some change in angle over a change in time. One thing I like to do, that I'm going to finish this off before we move on to the next video, is one of the ways I like to sort of think about this, because one of the biggest problems I see students having when we first get to this rotational or circular motion part of the course is kind of organizing in their head the difference between the linear and rotational speeds, and how to sort of conceptually think about it. So if you imagine an object that's traveling in a circle, we can describe it in terms of linear motion. And when you do that, if you're trying to sort of visualize and think about how that object's moving, I'll always think of myself as the object. I'm going a certain distance at a certain speed in a certain direction. All of those things, you're the object moving. When we're using these angular descriptions of motion, what you're really describing is, if you imagine yourself standing at the center of the circle that object's traveling in and pointing at the object, the angular position is, a measure of how far the angle you're pointing at is from some axes. The angular velocity is how fast do you have to spin to keep pointing at that object. And the angular acceleration is how fast is the rate you're spinning changing when you do that. So that's something I use to help organize my thinking with these. If you're talking about linear kinematics, or the linear position, velocity, and acceleration, kind of think of yourself as the object, and how fast are you moving, and how are you moving. If you're thinking about the angular stuff, imagine yourself at the center of the circle that the object's traveling around and pointing at the object, and you're describing how you're spinning in that case. Hopefully that helps. We'll discuss this more in the next video.